Good morning, students. लास्ट लेक्चर में हम लोगों ने डिस्कस किया था कि व्हाट इज कॉलम्स, व्हाट इज स्टड्स एंड टाइप्स ऑफ कॉलम्स, शॉर्ट कॉलम, मीडियम साइज कॉलम, लॉन्ग कॉलम्स एंड शॉर्ट कॉलम्स में फेलियर का किस तरह से फेलियर होता है उसमें डिस्कस किया था कि शॉर्ट कॉलम में जो फेलियर होता है वो डायरेक्ट स्ट्रेस, डायरेक्ट कंप्रेसिव स्ट्रेस और बेंडिंग स्ट्रेस की वजह से फेलियर होते हैं। आज हम लोग डिस्कस करेंगे लॉन्ग कॉलम्स के लिए। वैल्यू ऑफ ए लॉन्ग कॉलम। A long column of uniform cross sectional area A and of length L. Let us consider a long column of cross sectional area A and length L subjected to an axial compressive load P. Okay, axial compressive load P. Length of the column is L. A column is known as long column if the length of the column in comparison to its lateral dimension is very large. Okay, if the lateral length of the column is in comparison to the its lateral dimensions is very large, in that case columns are known as the long columns. Okay, uh, the long columns generally not fails due to the crushing alone. The failure will occur in the long columns due to the buckling. Okay, buckling or crippling. What is buckling? Uh, the lateral deflection about its length, the lateral deformation about its length is known as buckling. Okay, the load at which the column is buckles is known as buckling load or critical or crippling load. Okay, buckling load, एज्यूम कर लेते हैं P, और इसे हम कह सकते हैं क्रिपलिंग लोड ऑल्सो. Okay, area of the column is A, length of the column is L. Let maximum deflection is delta, maximum bending or deflection is delta, and direct stress is equal to sigma naught is equal to load upon area. Okay. So before determining the buckling load or crippling load for a given long column, some assumptions has been made uh, according to the Euler's theory for the columns. Now, firstly, assumption made in Euler's column theory. Okay. First assumptions for the Euler's column theory is the column is initially perfectly straight and the load is applied axially. Okay. So before calculating the crippling load, first assumption is the column is initially perfectly straight and the load is applied axially. तो जो कॉलम है हमारा वो पहले से पहला जो फर्स्टली जो है वो परफेक्टली स्ट्रेट है स्टार्टिंग में, और जो लोड है वो एक्चुअली यानी कि जो कॉलम का एक्सेस है उससे पास हो रहा है. ओके. द सेकेंड assumption, the cross section of column is uniform throughout its length. जो क्रॉस सेक्शन है कॉलम का वो यूनिफॉर्म है थ्रू आउट इट्स लेंथ, सेम है, कहीं भी डिफरेंट नहीं है. थर्ड assumption is the column material is perfectly elastic, homogeneous, and isotropic. And obeys Hooke's law. Hooke's law. Stress is directly proportional to the strain within the elastic limit. Next assumption for Euler's column theory. The length of the column is very large as compared to its lateral dimensions. Okay. Fifth assumption, the direct stress is very small as compared to its lateral dimension. Oh, it's is compared to the bending stress. Okay. The next assumption for the Euler's column theory is the column will fail by buckling alone. And the last assumption, the self weight of column is negligible. Okay, these are the assumptions for Euler's column theory. By the with the help of the Euler's column theory, we can determine the crippling or buckling load for the long columns. So the first assumption for the Euler's column theory is the column is initially perfectly straight, and the load is applied axially. Second assumption is the cross section of column is uniform throughout its length. Third assumption is the column material is perfectly elastic, homogeneous and isotropic and obeys Hooke's law. Okay, and the fourth assumption is the length of the column is very large as compared to its lateral dimensions. And fifth assumption is the direct stress is very small as compared to bending stress. And sixth assumption is the column will fail by buckling alone. And the last assumption is the self weight of column is negligible. Okay, these are the assumptions for the long columns. Okay, now there are four conditions for the end conditions of for the long columns. So for different end conditions, we have to determine the buckling and crippling load. Okay, and conditions of for long columns. So first end condition is when both the ends of column are hinged. Or pin jointed. Okay. Second end condition is both the ends of column are fixed. Third end condition is one end is fixed and other end is free. Okay, one end is fixed and other end is free. Fourth end condition is one end is fixed and other end is hinged. Okay. Now expression for crippling load. First end condition is when both the ends are hinged. Okay, when both the ends are hinged, determining the expression for crippling load. Okay, let us consider a long column of length L. A is the cross sectional area. P is the buckling load, a load at which column starts to buckle. Buckling load, the load at which buckling will start. Okay. Okay. So consider a column AB of length L A is the cross-sectional area of the column. Sectional area. P is the buckling load. Buckling load. Okay. So consider a long column of length AB. Sorry. Consider a long column AB of length L. A load, compressive load P is applied due to which column buckles about its length. Let us consider a section at a distance x from the point B, and the deflection at that point, that section is y. Okay. Now the movement due to crippling load at the section will be equal to the load into perpendicular distance, and this movement will be in anti-clockwise direction. So consider this movement as a negative movement. Okay. So here negative sign shows that the movement about the section is in counterclockwise direction. Okay. But from the flexural rigidity or from the deflection equation, the bending moment about this section will also equal to the EI d2y over dx square. If capital E is the modulus of elasticity of material, and I is the moment of inertia of cross section about its axis. This is the least moment of inertia. Okay. Now equating both the equations, equating the two movements, EI d2y over dx square will be is equal to minus p into y, or EI d2y over dx square plus p into y is equal to 0. Now divided by the EI, so d2y over dx square plus p upon EI y is equal to 0. Okay, this is a differential equation, and the solution of this differential equation of the above differential equation is y is equal to C1 cos x under root p upon EI plus C2 sin x under root p upon EI. This is the equation number 1. Here, where C1 and C2 are constants of integration. Now the value of C1 and C2 are obtained by the end conditions. Here first end condition is at x is equal to 0, the displacement or deflection is equal to the 0, because at the point B, the column is pin jointed. Substituting these values in equation 1, 0 is equal to C1 hello 0 is equal to C1 cos 0 plus C2 sin 0. 0 is equal to C1 cos 0 is equal to 1 and sin 0 is 0. So from here C1 is equal to be 0. Now applying the second end condition, at point A, x is equal to L. Here deflection is again equal to 0 because point endpoints are pin jointed. Now substituting this value, substituting these values in equation 1. So 0 is equal to the, because C1 is equal to the 0, so C1 cos L under root P upon EI plus C2 sin L under root P upon EI. Here C1 is equal to the 0, C2 sin L under root P upon EI. Okay. From here C2 sin L under root P upon EI equal to 0. From this equation, it is clear that C2 can never be equal to the 0, and for this for satisfying this equation. So if C2 is not equal to 0, then for satisfying this equation, sine L under root P upon EI should be equal to 0. Okay, because if C1 and C2 both are equal to 0, in that case equation will be equal to 0, deflection will be 0, but deflection is not 0 at each and every point of the column. So sine L under root P upon EI should be equal to 0, and sine will be equal to 0 where sine theta will be 0 at theta is equal to 0, pi, 2 pi, and so on. Now consider the first non-zero value. So from here sine, oh not sine, when L upon under root P, L under root P upon EI equal to pi, in that case sine L under root P upon EI should be equal to 0, or under root P upon EI is equal to pi by L, or P upon EI is equal to the pi square upon L square, or P will be equal to the pi square E into EI, E into I upon L square. Okay, so for a long column whose both the ends are pin jointed, in that case the buckling load will be equal to the pi square into E into I upon L square. Okay, now taking the second case, when both the ends are fixed, the ends are fixed. Let us consider a column AB whose both the ends are fixed, and the length of the column is and the length of the column is L. The crippling load for this condition is P, and column is buckled along the condition this like this along the length of the column. Now the moment of resistance at the fixed ends are m naught due to the fixed ends. Okay, consider a section at a distance x from the point B and the deflection at that point is y. Okay, let m naught is equal to the fixed and moments at A and B. Okay, now moment at the section will be equal to the m naught minus p into y. P into y is the moment generated by the load and m naught is the moment developed at the fixed ends. So the total moment about the section will be m naught minus py, but moment at the section m will be equal to the ei d2y over dx square. Equating both the moments from here, ei d2y over dx square will be equal to the m naught minus py or ei d2y over dx square plus py is equal to m naught. Now divided the equation by ei, so d2y over dx square plus p upon ei into y is equal to m naught upon ei. Okay, now multiplied by p and divided by p, so from here d2y over dx square plus p upon ei into y is equal to m naught upon ei, m naught upon p into p upon ei. Now the solution of this differential equation will be y is equal to c1 cos x under root p upon ei plus c2 sin x under root p upon ei plus m naught upon p. Now at x is equal to 0, y is equal to 0 and dy by dx slope is also equal to 0, and at x is equal to L, y is equal to 0 and the slope at these points are also equal to the 0. Okay, because both the ends are fixed. Now substituting these values in the above equation, 0 is equal to c1 into cos 0 is 1, sin 0 is 0 plus m naught upon p. So from here c1 is equal to minus m naught by p. Now differentiate the above equation, dy by dx equal to this c1 minus 1 sin x under root p upon ei into under root p upon ei plus c2 cos x under root p upon ei into under root p upon ei plus 0. So from here dy by dx equal to the minus c1 sin x under root p upon ei under root p upon ei plus c2 cos x under root p upon ei into under root p upon ei. So from end condition at x is equal to 0 dy by dx equal to 0. So c2 into 1 under root p upon ei so from here c2 under root p upon ei equal to 0. So under root p upon ei is not equal to 0, so c2 will be equal to 0, 0. Okay. Now substituting these values, y is equal to minus m naught p cos x under root p upon ei plus m naught p. Now applying the other end condition at x is equal to L, y is equal to 0, so m naught p cos L under root p upon ei plus m naught upon p. Now cos L under root p upon ei will be equal to the 1. So at theta is equal to 0 2 pi cos theta is equal to 1 when theta is equal to 0, 2 pi, 4 pi and so on. So taking first non-zero value L upon under root L under root p upon ei is equal to 4 pi, 2 pi. So from here p will be equal to the 4 pi square into I upon L square. So this will be the buckling load for a column whose both the ends are fixed. Here this equation can be